Hi everyone, this is Anna Bergstrom at Boise State University, and today we're going to dive into the Redox module, and we're going to start off with just a quick intro to Redox and how to balance redox reactions. And before we dive in, I just want to give a quick shout out to Nick Gubbins and Matt Ross at CSU for help putting this together. So overall, our module learning objectives are to balance a redox reaction and calculate its free energy yield, describe common environmentally relevant redox reactions, and be able to interpret and understand Pourbaix diagrams, which we'll learn a lot about in subsequent lectures. So for this particular lecture, what we're going to start in on is have the ability to define a redox reaction, identify the oxidation number of elements and compounds, balance a redox reaction both for mass and electron exchange. And just to give you guys a quick intro, you've probably learned about this in your Gen Chem class, but one of the classic, most flashy redox reactions is fireworks. So fireworks and all the different colors are just various elements going through redox reactions. But particularly for this class, what we're more interested in are more of the environmentally relevant redox reactions. So one of the places where redox occurs and is really important is in wetland environments. So if you've ever been near a wetland and you smell that rotten egg smell, that is redox. That's sulfur getting reduced. So what is redox? Redox stands for reduction and oxidation reactions. That's the full name for it. Any reaction where electrons are exchanged from one atom to another constitutes a redox reaction. One way that you can remember it, you've probably heard lots of different acronyms, but one of the ones that we'll use regularly is oil rig, which basically stands for oxidation is loss of electron and reduction is gain of electron. So you can always come back to that. Once you memorize that acronym, you'll be able to figure out which is the oxidized component of the reaction and what part is the reduced component. So atoms that gain electrons are reduced, and atoms that lose electrons are oxidized. And again, these are all paired reactions, and we'll go through this in great detail with a couple examples. So it's just like two sides of the same coin, and these electrons need to come from somewhere. So because they're paired, they naturally have to be paired reactions. If we're going to gain electrons in one place, they have to come from someplace else. So that's why we always have paired reactions. And the important thing why we care about redox, and particularly in the environmental setting, is because this is energy exchange, and this is critical for a lot of metabolic functions and maintaining life. So again, just as a nice example with this diagram of how redox reactions are paired reactions, we have this electron acceptor. So this is the molecule that's going to gain an electron, and we have an electron donor, the molecule that's giving away its electron. This electron is donated and then goes to the electron acceptor and results in a reduced product, and the donor that gave away its electron is the oxidized product. Remember, oil rig. So for this specific example, our electron donor is our organic carbon. Our electron acceptor is iron 3. It gains an electron and becomes iron 2. And our oxidized product from our organic carbon is CO2. So the key concept here is a redox reaction occurs when electrons are exchanged between atoms. Then they occur in a paired fashion. So in order to understand what's going on, we need to be able to balance redox reactions. So this is probably something that you got in Gen Chem, but for some of you it might have been a while, so we're going to go back and review how this works. And we're going to look at two examples. The first is lithium in water. Lithium in water is really scary and rather explosive. So we'll look at the redox processes that cause that. And then we're going to look at denitrification as an example here. So in order to balance redox reactions, we have to track the oxidative state or the oxidation number and how that changes from reactants to products. And it's tracked by the individual atom, not the molecule as a whole, and this will make more sense as we go through this. Raising the number of an individual atom means that it was oxidized, and similarly, if we reduce the number, makes sense, checks out, the atom was reduced. So how do we know if and when the oxidation state of this atom changes? Well, if we have a deep understanding of physical chemistry, we would inherently know because we understand how our physical chemistry works, or we can apply redox rules. So we're going to step through those redox rules now. The first rule is that self bonds, the oxidation state is 0. So for example, oxygen gas, hydrogen gas, nitrogen gas, oxidation state is 0. If we are dealing with a monatomic species, that equals its charge value. So monatomic ions have an oxidation state of their charge. And so if we're dealing with aqueous solution, our solutes in our water are going to take this form, and it's very straightforward to understand what the charges of those. So sodium ions in solution have a oxidation state of +1. Similarly, chloride has an oxidation state of -1. Magnesium is +2. So rule number 3, alkali metals are always +1. So these alkali metals here always have an oxidation number of +1. Our lithium, sodium, potassium, rubidium, cesium, and francium, if we're getting that crazy. Rule number 4, alkaline earth metals, just the next one over on the periodic table here, has a oxidation number of +2. So these classic ones you think of, beryllium, particularly magnesium and calcium, but then moving down to strontium and so on. They will always have an oxidation number of +2. So just keep the alkaline and alkaline earth metals in mind for rule 3 and 4. And why and how does this work? Well, the answer, the physical chemistry explanation for this is valence. So remember, we have our electron shells here, and if we look at lithium, its first shell is filled with 2 electrons, but its next one out has this +1. So this +1 charge, and this electron is very unstable here and has a tendency to be pulled out of this lithium ion and is highly reactive. Same thing if we move out to these larger molecules, again, because this is an alkali metal, potassium, we have more of our orbitals filled, but here we have this lone electron out in this farthest out shell that has a tendency to be donated. Over here, these are alkaline earth metals with beryllium having a charge of +2, so these are going to want to be donated, and same down here for these larger molecules like calcium, charge of +2. So that's how those work. Rule number 5 is hydrogen. Hydrogen can be either +1 or -1, and it is +1 when bonded to a non-metal and -1 when bonded to a metal. And you might ask yourself, how do I know if it's a metal or a non-metal? Well, you can go back and look at the periodic table, and they are designated as what are metals and what are non-metals there, and that will give you a pretty good hint. So, rule number 6, oxygen is usually -2. So this is almost always the case that oxygen is -2, and particularly environmental conditions, it's a pretty safe bet that oxygen is -2. With the rare exception, we might run into peroxide, in which case it is -1. Finally, rule number 7, fluorine is quite scary. It has an oxidation state of -1 all of the time, and it is very highly reactive. Think about HF. We've talked about this before, how HF can be a very scary acid to work with and will eat into your body and burn your bones. So it's a very strong oxidizer and always -1. Okay, rule number 8. Charge is the sum of the oxidation states. So the sum of oxidation numbers in a non-charged molecule is 0, pretty straightforward. And the sum of the oxidation numbers in an ion is its net charge. So I'm just going to click through here. So we have these examples. Sodium chloride. We know by rule number 3 that sodium is in that +1 category, and then we know by looking at this that it has a net charge of 0, which hints to us that chloride must have an oxidation state of -1. Over here with sulfate, we know that we have a -2 here, so each oxygen is -2. Remember, that is almost always the case in environmental conditions, and that's true here. Our oxygen is -2 by rule number 6 because we have 4 oxygen molecules. -2 times 4 is -8, and if we see that we have a net charge of -2 here, we can infer that sulfur is +6. Okay, so why are we doing this? We need to track oxidation numbers because this is a proxy for tracking our electrons. And remember, the donation and acceptance of electrons is at the root of our redox reactions. So again, raising the number of the oxidation state means that the atom was oxidized. And this is not always, but generally in environmental conditions, the atom that forms the new bonds with oxygen is the one that's going to be oxidized. Reducing the number of the oxidation state means that the atom was reduced. And again, just as why are we going through this? And you may be having some bad memories from Gen Chem, just keep in mind that maintenance of life depends on redox, and when we're working in environmental conditions, this is incredibly important. I mean, it's important no matter what, but what we care about particularly is maintenance of life in environmental conditions. So, key concept. Oxidative states are a tool that allow us to track the movement of electrons in reactions. So, we are going to go through and balance redox reactions and our general steps. And what we need to do here is we need to balance our chemical reaction by mass. This is something that hopefully you all are very comfortable doing with at this point in the semester. And we need to balance the electrons. So this is a bit new to us, but we're going to go through some examples and step through how this works. So to balance our redox reactions, we have to break them down into half reactions. So our oxidation half reaction and our reduction half reaction. So let's go back to these examples and actually go through them. Again, we're going to look at lithium and then denitrification. So starting with the lithium. First, what we're going to do is, again, we are tracking elements, not entire molecules, and we first need to determine its oxidative state. So lithium, again, we can see that we have 2 of them, and our lithium, because it's not charged, we have an oxidation number of 0. Now we need to break apart our water molecule. Again, by rule 6, we know that oxygen has -2, and then our hydrogens, because we have a net 0 charge here, we know hydrogens are bonded to a nonmetal. We have a charge of +1 times 2. Our hydrogens have +2. So our total electrical charge is 0. Okay, moving on to this product side of a reaction, we have 2H2. It's self-bonded. It has no charge, so 0 is our oxidation number for our hydrogens. Then if we break apart our LiOH, we have lithium is +1, again, because it's one of those metals. Our oxygen is -2 by rule number 6. And then we can determine that our hydrogen is +1 because we have a net 0 charge over here. So our total electrical charge for this half of the reaction, if we 0 + 1 + 1 - 2 is 0. So we can determine here that our lithium loses an electron because our oxidation number increased from 0 to +1. We can see here we started out at 0 and now we have +1 over here. So that was the thing that was oxidized. Our hydrogen gained an electron. See, we can see here that we had, we went from +2 to 0 over here. And we know that our hydrogen was reduced by gaining that electron. Now that we've tracked our oxidation states, we can balance each of these half redox reactions and then finally put them together. So we need to split our redox into our reduction half reaction and oxidation half reaction. So the first thing that we're going to do, how this works, is we're going to balance the elements in the equation other than oxygen and hydrogen first. Then we're going to balance our oxygen atoms by adding water molecules to the opposite side of the equation. And on that same side of the equation, we're going to balance the hydrogen atoms, including what we added in our waters, by adding hydrogen to the opposite side of the equation. And then we're going to add up the charges on each side, and if we don't have equal number of charges, we're going to have to add electrons to the more positive side. And just to note, our hydrogens and our electrons are almost always on the same side of our equations. And then keep in mind our electrons must be balanced on each side of the equation. And then we can add these half reactions together and cancel out the electrons and other common terms. So that was a lot of steps, and we'll walk through with an example how that works. So we're going to start with our oxidation half reaction, where we have lithium going to LiOH, again because lithium was the thing that was oxidized. So first thing we do is we have our lithiums balanced, so we go into balancing our oxygens by adding a water molecule here, and now you can see we have 2 hydrogens on this side and 1 hydrogen on that side. So we need to add 2 hydrogens over here, and then to keep this balanced in terms of charge, we can see that we have +2 over here, so we're going to need to add 2 electrons over here. And that is our balanced oxidation half reaction. So now we can move over to the reduction half reaction. So we're starting with again, remember our this is our half that got reduced, so we have water going to hydrogen gas, and so we don't have any other thing that we can balance before we get to balancing our oxygens. So in this case, we are adding a water to this side. And now we need to balance out our hydrogens. Again, we have 4 hydrogens on this side of the equation, so we need to, and 2 hydrogens on this side of the equation, so we need to add 2 hydrogens to make 4 hydrogens on either side of the equation. And then we need to balance our charge. So we had a +2 charge because we have 2 + 1 hydrogens, so we need to add 2 electrons on this same side of the equation. So now that we have our half reactions balanced, we can combine them together. So again, here is our oxidation half reaction and our reduction half reaction. And we can see that our waters are canceling out on either side of our equation, our hydrogens are canceling out, and our electrons are canceling out. So we've gotten back to this side of the game. And we need to balance for mass here. And in this case now we have both, when we add our mass balances in the appropriate place, we can see that we have both mass and electrons balanced. And again, our lithium was what got oxidized and our hydrogen was what got reduced. Okay, so one more example, we can look at our denitrification equation. So what this looks like is we have 2 nitrates. This is a simplified version of sugars, and we have hydrogen ions over here, and then as a product we have nitrous oxide, carbon dioxide, and water. And this is the reaction for partial denitrification. So is most of you know, CO2 and nitrous oxide are a greenhouse gas, but nitrous oxide is a particularly potent greenhouse gas, so we generally do not want partial denitrification to occur, preferably. It gets all the way to N2 gas, but that is not always the case. Okay, so we are going to step through how this works, and the first thing that we need to do is figure out the oxidation number of each of the reactants. So, starting with nitrate, and remember, we can't just look at the molecule as a whole, we have to look at each individual element within that molecule. So for oxygen, we know by rule 6 that our oxidation number for oxygen is -2, and we have 3 of those oxygens, so 2 times 3 is -6. And then for nitrogen, we have a +5 from our nitrogen, which is net -1 because we have this minus charge over here. So we can infer to get a -1 from our -6 that we need a +5. Okay, moving into our sugars, again, oxygen is -2, very straightforward. We have 2 hydrogens, which is +1 because we are bonded to nonmetals here. And since we have 2 of them, we have 2 +1s. And then with our carbon, again, we need to balance this out. We have a -2, a +2, and we know our net charge is 0. So in this case, our carbon has an oxidation number of 0. And our hydrogen here on the end, we have 2 hydrogens. Those are each +1, so our hydrogen has a charge of +2. And if we balance this out of our total electrical charge from each of these components is -0. Okay, or is -0, is 0. Our products here, stepping through each of the elements in our products, with our nitrous oxide, oxygen again is -2. Our nitrogen we know is +1 because we have a net 0 charge here. So we have 2 +1 nitrogens equals +2. Our oxygen in CO2 is -2. We have 2 of them, so our oxidation for all of our oxygens is -4. For carbons, we know this needs to balance out our oxygens, so we have carbon is +4, and our oxygen in our water is -2, and our hydrogens are +1, and we have 2 of those, so that's +2. And our total electrical charge on our product side is 0. So, figuring out what's going on, what's being oxidized, we can see our carbons over here. Our carbon in this row here had a oxidation number of 0 in our reactant side, and then when we move to our product side, we can see it has +4. So our carbon was what lost electrons, and it was oxidized. We increased that oxidation number, so we know it was oxidized. And our nitrogen was what gained the electrons. You can see over here that our nitrogen was +5. And then on our product side, it is +2. So it was reduced from +5 to +2, gaining electrons. So we know the nitrogen was what was reduced. So we can split these up into our half reactions and go ahead and balance those. So our half reaction, again, our carbon was what was being oxidized. So we know we started out with carbon in our sugar and it moved over to being CO2. So we can start working with this equation. Our carbons are balanced. So our next step would be to add in this water because we had 1 oxygen over here, 2 oxygens over here. So how we balance it is by adding water on this side. Then we need to balance our hydrogens. We originally had 4 hydrogens here because we had 2 in our sugars and 2 in our waters. We had no hydrogens over here, so we need to add 4 hydrogens on this side. And then we need to balance out the charge. So because we had just 4 hydrogens chilling out on this side, we need to add 4 electrons to balance out those positive charges from the hydrogens. Okay, so now we can move over to the reduction half reaction. And again, our nitrogen was what's getting reduced, and it started off as nitrate and moved to nitrous oxide. So we will put that in our reduction half reaction where we had 2 nitrates moving to dinitrogen gas. So again, we already have 2 nitrogens on this side and 2 nitrogens on this side. So now we need to balance out our oxygens, and we do that by adding water. So we had 3 oxygens here and 1 oxygen here. So we need to, we had 2 times 3 oxygens here, which is 6, and 1 oxygen here. So we need to add 5 waters to make 6 total oxygens on this side. And then because we had 5 times 2 hydrogens, when we added those 5 waters in, we need to add 10 hydrogens on the other side to balance out our hydrogens. And now we're moving into balancing our electrons. And so again, we had 10 positive charges here, and because we have 2 nitrates with a -1 charge, that is -2. So our 10 minus 2 gives us a positive 8 charge, and we balance that out with 8 electrons with our negative charge. So now we can combine these half reactions, where we have here is our oxidation reaction up here, and here is our reduction reaction that we're moving down here. We can see, because we had 4 electrons in our oxidation reaction and 8 electrons in our reduction reaction, we are not balanced for electrons yet. So we need to multiply everything by 2 in this reduction half reaction our oxidation half reaction to get us to balanced electrons. So moving backwards, just to finish this off, we have 2, we balanced our electrons, and then we can add them together, and we can see what cancels out here. Our electrons are going to cancel out. 2, our hydrogens are going to cancel out, except for 2 hydrogens on this side, because we have 8 hydrogens over here and 10 hydrogens over here, and we end up with our nitrate, our sugar, and our hydrogen on one side, our CO2, our nitrous oxide, and our water. Of course, our waters are canceling out over here. We have 2 waters on one side and 5 waters over here, so we're left with 3 waters on the other side. Okay, so as we've walked through these extensive examples, we can take home this key concept that our redox reactions need to be balanced by electron exchange and molar mass. It's not sufficient to just balance them by molar mass. We need to make sure that our electrons are balanced too, and that allows us to identify what is being oxidized and what is being reduced in this reaction. And that is all we have for you, and we will pick it up in the next lecture.